Welcome back, everyone, to the last video of the first chapter. Getting started, we're going to be working with similarity this time, and thought I'd kick it off with a problem that probably represents something near and dear to all of you, walking from the high school to the mobile, a trek I've seen many of you make way too often. And so it shows here on this little snippet that I took off of Google Maps how far it is. And it says it's a 20-minute walk, but I want to know how far I have to walk in that 20 minutes. On the page here, this looks like, just a couple inches. Oh man, it's only a couple inches to the mobile. No, of course not. This is a scale, what we call a scale drawing. It's taking something from the real world and fitting it onto a piece of paper. We can't fit the entire world onto a piece of paper, so we have to shrink it down to make it fit. And in order to do that in a meaningful way, you should always provide a reference, or what's literally called the scale or the legend, to tell the reader of the map how big things are, on your map, like how much space. In this case, let's actually do this. If I try to line this up with that little thing right there. So I'm looking at those little marks that kind of go vertical, these pieces. And it says that much space on the map represents 500 feet in the real world, right? I'm about 6 foot. So, about 90 of me is how far would fit. You could fit 90 of me head to toe in that much space on the map. If you scaled me down the same way they've scaled the world. If you ever zoom out on your map, that scale adjusts. You'll see it in the little corner, kind of doing this like shrinking and growing things as the numbers change. Because as you zoom in or zoom out, it changes, how much of the world you can see. So they have to change the scale. Well, on this paper, you can't really scale too well on the paper. So the scale is locked in, and I can actually measure. It looks like it's about 1.5 centimeters. So like here's 1 centimeter, here's 2 centimeters. Let's call it about 1.5. I'm having a little trouble lining it up. About 1.5, I'd say. So 1.5 centimeters is equal to 500 feet in the real world. 1.5 centimeters, this much space on my ruler or on the paper represents 500 feet in the real world. So the question then becomes is how far would you have to walk to get from the high school to the mobile? Well, first off, just to simplify this, I'm going to kind of count this little squiggly bit as a straight line. And then obviously this part's pretty straight. Once you hit the sidewalk, you just go straight on over. Well, if I wanted to know how far I'd have to walk in the real world to get from the high school's front doors to the mobile, I would just measure those parts. So this is about 3 centimeters, give or take, on the map. And this part right here is about 13 centimeters. Oh, you can't see that. From where we turn at the sidewalk to the mobile is about 13 centimeters on the map. So that's a total of 16 centimeters that you have to walk on the map. But then we need to scale that to how far it is in the real world. So we use that scale in order to convert this 16 centimeters of paper into a distance it is in the real world. So you might remember from 7th grade maybe, when you learned about proportions. We can use proportions to solve problems like this too, to find out how far it actually is. And you would just use that scale you have. If 1.5, call these the centimeters and these the feet. 1.5 centimeters is about 500 feet. We know that from our scale. Then we can use the distance we just measured, 16 centimeters, to find X amount of feet. There's a couple different ways you can go about this, but the way that's typically taught is called cross-multiplying. If you multiply those, it will always be equal to when you multiply these, which is kind of handy to do. So you set the fractions equal to each other because it's this much distance is equal to that much distance. This much on the map is equal to that much in the real world. And so therefore, if you cross multiply, you can get rid of fractions. So it comes out as 1.5x equals 16 times 500, which is 8,000. And then you just solve for x by dividing. So I get x by itself right there. X is about 5,333 feet. By the way, 5,200 feet is a mile, so it's just a smidget over a mile from the front doors of Hamilton to the mobile. So for any of you runners out there, if you're looking for a good way to measure some distance, do laps back and forth between the high school front door and the mobile. It's about a mile each way. Better problem would be how many calories of that Bang energy drink do you burn off in the walk back and forth from the high school to the mobile? Not enough. See if you could set up a proportion to solve the second part of this as well. Go ahead and pause and try to work out a proportion. Set up a proportion for 5 snacks for $12. How much would 3 snacks cost? Go ahead and set up that proportion and try to work that out now. I was pausing it to go ahead and work this out. I want you to see how I set it up. So just in case you're unfamiliar with this process, 5 snacks. So these are my snacks. This is my cost. 5 snacks equals $12. So then if this is snacks and I'm buying only 3 snacks would be X amount of dollars. So the way the cross multiplying works, just so that I feel better about teaching you this trick, if things are equal, you can multiply both sides of the equation by something. So you start out by multiplying by one of the denominators, and essentially what you have here is 5 divided by 3 times 3. So that just cancels off when you do that. And all that really gets multiplied is this side. And then you do the same thing with an x, weirdly enough, is you multiply this and this by the unknown number x. And here you have 12 times 3, 36. And then that's being divided by x and times by x. So just the way that we divided off the 3, we can cancel out, or cancel the 3, we can cancel out the stuff that's on the same side. And it just really what ends up happening is you get 5x equals 36. So the shortcut that middle school math teachers love to show is the butterfly method or whatever, the cross multiplying, where you multiply these and set it equal to that. And God forbid you ask why you do that, because they'll slap you in the face and say, just do it. Right? That's what middle school was like? Just me? Okay. Finishing, then you divide by 5, and you get $7.20, because I already did the math. Bippity boppity. 36 divided by 5 should be $7.20. So that's proportions. We are going to use this a bunch with your city map, this unit, because you need to make sure that you have a scale. You can't just be like, this is my road and this is my high school. It's like, oh, cool. So either these things are right next to each other, or you have like a half-mile long high school. Like, that's insane, right? Like, if you actually look at it, the high school is all this right here. Like, that's the whole high school pretty much, because these are the roads that drive out and around it. So like, you need to make sure that you're keeping things in mind. I've had people before that will draw their roads this big and draw their buildings like this big. Like, the road is the size of the high school. That's crazy. So as you set up your map for your city, you're going to want to make sure you're paying attention to your scale and thinking about what different links the length of lines means in a real world scenario. I've had people also who make their map, 5 miles wide. If you're zoomed out that far, you're not going to be able to see any buildings. Like, this is 1 mile, and we have a little bit of a view of the high school, but like, imagine if this was 5 miles, the high school would be that big, like a dot like that. All of your buildings would be just points. So you're going to want to make sure you're thinking about how far you're zoomed in or out. You also don't want to have a scale that's so small that you're just like crazy zoomed in on it. You've got to find a good balance. And we'll talk about that more in class. So I'm not going to talk a ton about the rest of these. I'm going to want to just give you a chance to pause and see if you can work through them. And then I'll go over kind of my solutions and my thoughts here in just a minute. All right. So first one talks about ratios. Ratio is a comparison between two things. So 4 to 7 goats to sheep. So that means for every 4 goats, there are 7 sheep. Another way you could rewrite that is that 4 plus 7 is 11. So 4/11ths of the animals are goats and 7/11ths are sheep. Right? You can add them together to get denominators instead of a ratio. If you prefer thinking about it as a fraction, that's another way of going about it. For here, though, it's easy to set up that for every 4 goats, you have 7 sheep. So X amount of goats would give you 28 sheep. Some of you might have realized that's just 4 times as much. So this is going to be 4 times as much. That's awesome if you did that. Otherwise, you could cross multiply and see 7x equals 4 times 28 is 112. So then you can just divide like we did before and get 16. When you go to set this up down here, out of 280 cars that they checked, there were 4 defects. So then out of 10,500 cars, we would expect X amount of defects is how I would want to set that up as a proportion. So then I have 280X. If you multiply these, you get 42,000. So divide, and you'll find that there should be about 150 defects out of all 10,500 cars if 4 defects were found in 280 cars. Yeah. So this is a very widely used thing in statistics. It's called sampling. If you don't want to check all 10,500 cars, you just have to make sure that you're checking random cars and not 4 cars back to back or something like that. Because, maybe there was just a couple defects right in a row, and that's going to make you think, all the cars are defected. There was just a problem for a little bit. So as long as you randomize the ones you choose, you can do what's called sampling. Instead of checking everything, you just check a few. Another map problem. So if 1 inch is equal to 5 miles, 0.75, I just did 3 divided by 4. Hey, crazy thought, fractions, they're just division. 3/4 is 3 divided by 4. So if you don't like fractions, just divide and get a decimal. That's what I did. Again, cross multiply, and this time I get 1x, so I don't have to do any division. 1x is just x. 5 times 0.75 is 3 3/4 or 3.75 miles. And then finally, if I have 1 inch is 12 feet, the actual building, so make sure you're setting these up carefully, that it says here on the map, it's 3/4 inches, so I wanted to put that on the inch side. Here, I know the actual size of the building, so I want to put that on the actual size. 1 inch is 12 feet. This is the real world size. This is the map or the scale, the thing that's smaller, fits on the paper. So the 114 goes on the right this time, and I get 114, 12x, divide by 12 to get 9.5. Maybe you didn't use proportions. Maybe you just kind of thought, I multiply, I divide. Perfectly fine. Proportions are there to help you set it up if you're a little stuck or confused, but by no means do you absolutely need to do that or need to use them. All right, we're getting into similarity now, which is basically just scale factors, making things bigger and smaller, but with shapes. So I put these little symbols here. If you haven't seen them yet, they just mean that the angles are equal. So like this angle, the 2 arcs goes with that angle there, the 2 arcs. That angle goes with that angle, and therefore this angle goes with this angle. So similar just means like on Google, when you take, or a Google Doc, if you take the corner of a picture and push it in, it just shrinks the whole picture. It doesn't squish it. It just makes the whole thing the same picture, but smaller. Compared to if you grab the top or side, it actually stretches and squishes the picture, distorts it. But similarity means that all of the angles will stay the same, and all the sides, will be multiplied or divided by the same amount. So, for example, here it's called the scale factor, how much you multiply or divide each side by. If this angle goes with that angle, and this angle goes with that one, the one between them. So yeah, this needs to actually be kind of turned around. See how this is backwards from that one? So this side goes with this side, the 8 and the 12. And then the one between them unmarked and the double angle, 9 and 6. So those guys go together. And then that leaves these 2 to go together. So basically what I'm saying is that each one of these numbers has been multiplied by some unknown number called a scale factor to get these numbers. But that scale factor has to be the same for all of them. Otherwise, it would be distorted, like I was saying, stretched and squished kind of thing. So to make a 6 become a 9, what you can do is just divide to get backwards. And I say get backwards. If I divide those, 9 divided by 6 is 1.5. So what that means when I say get backwards or go backwards is if I multiply 6 times 1.5, that's how I get to 9. See how I kind of worked? But I used division to undo the unknown multiplication. Since I didn't know what I had to multiply each of these sides by to get these numbers, I took the bigger and divided by the smaller, and it told me the scale factor. So now I can use that to double check the rest of these. If I do 18 divided by 12, I'll get 1.5 again. If I did 12 divided by 8, I'd also get 1.5. So each of these sides has been multiplied by 1.5 to get the larger side, to get the sides of the larger triangle. So that's called the scale factor, and it's how you can check to make sure things are similar. Same thing happens again here. I actually know that this angle is going to match up with that angle because they're vertical angles, so they're not marked like they are here. I have to use a little bit of knowledge from earlier this chapter. Since these are vertical, that means these are the angles that line up. I don't put this angle up here and turn it over. If I was going to line this triangle up inside of this one, it would go angle C down here, angle A, and angle B. I would kind of rotate it around because it has to line up like that. And obviously I know it doesn't reflect over because then it'd be pointing down and that one's pointing up. So it has to rotate around. So this angle goes with this one goes with this one, and that one goes with that one. Yeah, hopefully that makes sense. So you kind of need to know that so you know which sides line up. That tells me the 6 and the 10 go together. So 10 divided by 6 has to be the same thing as the 15 and the 9. 15 divided by 9. If these are going to be scale factors of each other. And 10 divided by 6, I'll just leave it as a fraction. That reduces it to 5/3. And both of those reduce to 5/3. So that would be my scale factor. Just like 1.5 was my scale factor here, 5/3, or what is it, 2.6 repeating, 1.6 repeating, is our scale factor for these problems. So you just divide these similar sides in order to find your scale factors. Okay. I'm going to ask you to pause on number 8 and try to work through setting that bad boy up. So try to draw out the two triangles, and then we'll work on figuring out whether or not they're similar or what the scale factor and the missing sides are. So see if you can set up the triangles yourself, and then we can look at finding the missing angles and sides together. Ooh, if you got that, good job. I actually don't know what the shapes look like. I kind of tried to approximate it, just like guessing a little bit. That this side's tried to draw it a little bit shorter than this side, and this side's a little bit shorter than that side. But I don't know exactly what these shapes were, and I didn't want to take the time to measure them out. So because I don't know these are centimeters or inches or miles, what they are. So I could have, but here we are. We'll figure out the problem regardless. What is important though is to figure out what matches up with what. So in this triangle, and I might have wanted to have told you this beforehand, the order that the letters go in is very important. So the fact that A, B, C, and then D, E, F, what that means is that angle A matches with angle D. So this angle matches with that angle. I'm sorry, I didn't mention that before. B matches with E. So then angle B is in the same spot as E, and C matches with F. So I know that this angle is equal to this angle, and this angle is the same as this angle, and this angle is the same as that angle. So I can actually go ahead and copy those over as some of the missing angles so that B and E both have to be 40, and F and C both have to be 30. So again, the idea that similar pictures, the shape itself doesn't change, just the size of the shape. Right? So as I do that, I could fill in the space between my thumbs and fingers and have a bigger triangle, but the shape of the triangle isn't changing. That's the idea of similarity. Again, think about a picture in a Google Doc. If you grab the corner and drag it, the picture doesn't change, just the size of the picture. Whereas if you actually drag a side, it squishes the picture and kind of makes like a new picture. It's different, right? So the idea here is that we're not changing the angles, just the side lengths. And we're all multiplying them by the same amount. They're getting scaled up or scaled down, depending if you're stretching it out or smaller. So what we need to be able to do to find those missing side lengths then is use two of the sides that correlate or go together. AB, see in the AB and DE are in the same locations compared to like BC and EF. So BC is going to go with EF. But I don't know what BC is yet, and I don't know what my scale factor is, so I can't really get it. What's key to this problem is knowing both of these sides. This is what allows you to find your scale factor. Going 20 divided by 8 is 2.5. So our scale factor, to make an 8 become a 20, I have to multiply it by 2.5. So then the question becomes, what do I multiply by 2.5 to get 30? What times 2.5 gives me 30? Well, I can reverse engineer that and just divide by 2.5. Divide by 2.5 to find what this side over here is. That's my unknown. 30 divided by 2.5 is 12. Yeah. So this side, BC, would be 12. And again, I found that because it has to be multiplied by the same thing that 8 is being multiplied to get to 20. And I know that it ends up being a 30. So I can divide to get back to it. This side, I can go forwards because I know the small side down here is 10. 10 times 2.5 is 25. It kind of makes sense. This is the smallest, a little bit bigger yet still, kind of like on this one over here, the way I tried to draw. And the final piece, you might not have remembered this, but every triangle, the angles add up to 180. You probably heard that in middle school at some point. If not, hey, every triangle's angles add up to 180. Crazy, right? So since we know 40 and 30 already is 70, this angle down here has to be 110 degrees in both of them because that's what adds up to 180. Woohoo! We're having fun now. All right, last couple. If you want to pause and work ahead, feel free. I will warn you that this one gets a little bit tricky, as if the rest of them hadn't been already. So let's go ahead and jump right in and check it out. We've got this smaller triangle down in here, which imagine if you like grab that corner and drug it out here, it would scale out to be the same thing. So again, it's like that idea of a picture in a Google Doc is that you can just grab it and drag it out to make it larger. So these are similar, but the thing you have to think about, the trick here, is you only see 9 and 3, but the side length of this actual big triangle is 12, the 9 plus the 3. So you're taking a small triangle whose side length is 3 and stretching it to make a side length of 12. That means our scale factor here is times 4. We're scaling that tiny little triangle in there out to be 12 units, inches, feet, whatever, instead of just the little side, which is 3. So we're scaling by a factor of 4. Well, I can find out why real quick from that then. What number times 4 would give me the 12 out here? Well, y times 4 is 12. Yup, you guys are already ahead of me. It is 3. So that means this is an isosceles triangle, if you know that term. It has two sides that are the same. But we don't know what this one is down here yet. And this is the part that gets tricky, is because I don't know what the full length is, nor do I know of the big triangle, nor do I know what the small one is. It's a variable, x. I know the big one, ready for this, is 15 plus x. And in order to get that, I take the small side and multiply it by 4. Ooh, we setting up equations in here. 4x is equal to x plus 15. To solve that, subtract the x over, which now means that 15 equals 3x. Divide by 3, x equals 5. Is that right? 5? Yeah, 5. Ocho is 8. That's a 5. Spanish. Last one. If you've got, you can actually do this in real life. If you want to know how tall something is, stand near it. And if you know your height, you can make a similar triangle to find out that thing's height just by measuring your shadows. So the sun's casting a 4-foot shadow on my 5 feet of height, and it's casting a 10-foot shadow on the tree's X amount of height. So if tall shadow, I am 5 feet tall and have a 4-foot shadow, tree is X tall and has a 10-foot shadow, 4x equals 50. That means the tree is about 12.5. Oof. Paper moved. Feet. 50 divided by 4, 12.5. Woo! Math o'clock up in here. We doing stuff. We mathing. Math's so hard. Hopefully this makes sense. If you have any questions, as always, send me or Mr. Sheridan an email. Talk to us. Let us know how we can help.